In this video, we're going to talk about flavin-dependent monooxygenases that require an external reducing agent. So, there's two things that must happen. First, diatomic oxygen must be activated. Okay, and once the oxygen is activated, then it can be transferred to the substrate. Okay, so let's look at these kind of piecewise. Okay, so O2 activation. The O2 is activated by flavin. Okay. Now, flavin can be either FMN or FAD, but flavin, on the other hand, is activated by NADH or NADPH. These are essentially the reducing agents, external reducing agents. So this is an external monooxygenase we're talking about here, right? Okay, so this reaction here kind of depicts the activation of flavin by NADH. So essentially what happens is the FMN or FAD gets converted to FMNH2 or FADH2, the reduced form of them, okay, by NADH acting like a reducing agent. Okay, that's pretty straightforward. I believe we looked at some of the mechanisms of that in the past. More importantly, what I wanted to talk about for this particular reaction is O2 transfer mechanism. Okay, as we'll see, a very common motif is the flavin hydroperoxide intermediate in these types of reactions. Okay, we'll see there are actually well, here's the structure of the flavin hydroperoxide. Here's the hydroperoxide piece. We saw this in the last video on lactate oxidase, right? This was an important intermediate. So essentially, though, there's two classes of reactions. One in which the substrate acts like an electrophile or is an electrophilic. Okay, that was an example. That was the lactate oxidase. That was the last video the last video in this series. Okay, but also the substrate can also act like a nucleophile. Okay, or be nucleophilic. Okay, and let's look at an example of that. Okay. So here's a mechanism of oxygen transfer. Here's the flavin hydroperoxide. Okay, this reaction is essentially a nucleophilic or an electrophilic aromatic substitution reaction. So what happens is the electrons come out of here and attack this oxygen. This oxygen here is partial plus, and this oxygen here is partial minus. So there's a partial plus charge on this oxygen. This is really the first step of an EAS, electrophilic aromatic substitution. Okay. When that happens, this bond here breaks, and these electrons attack that hydrogen right there to generate this hydroxy flavin intermediate. Okay. So that goes on, and as a result of this electrophilic aromatic substitution, normally, if you go back and look at some of the mechanisms of EAS, after this step occurred, there'd be a plus charge right here. To stabilize that, remember cations aren't very stable, there's an adjacent base on an enzyme or on an amino acid that deprotonates here, and these electrons drop in there at the same time. Okay, that's why I showed this carbonyl or carbon oxygen system over here like that. Okay. The hydroperoxide flavin then releases the hydroxide group and becomes FAD. A mechanism that kind of accounts for that would be kind of something like this. And kicks out that hydroxide ion. Right. That regenerates the FAD. Then NADH or NADPH could re-reduce this and go on to another reaction. Okay. But our substrate now has one hydroxy group that's been incorporated into it here. Okay, so the next step of the reaction is the typical elimination step that we see in electrophilic aromatic substitutions. This proton is removed by a enzyme-bound base. Those electrons fall in and flip back out to here and grab that hydrogen there to give us our dihydroxylated compound. Okay, this was just an example substrate that I chose to look at. Okay. So you'll see though that in this reaction, the substrate is nucleophilic. See how the electrons are flowing out of the substrate into the Flavin hydroperoxide, or I'm sorry, Flavin hydrogen peroxide. If you go back and look at the lactate oxidase, you'll see that it was reversed here. In those cases, the electrons flowed out to the substrate. Okay, so this is an example of the nucleophilic case. So evidence for this mechanism comes from a Hammett correlation. This is actually a pretty neat study. So what they did was they synthesized a variety of different Flavin derivatives, or they put different X groups here. So that's FAD or FMN. Okay, so they put these different X groups here. And you'll recall from a Hammett correlation, if they plot the log of the rate, let's make it an R, the rate with FADX versus the rate of the unsubstituted FAD, and plot these against Hammett sigma constants. These are Hammett constants. Okay, they saw a line like this, has a negative slope, so rho is less than or equal to 1. Okay. Now, typically that means that we're invoking a cationic mechanism. Remember the way this works. Down at this end, this is electron withdrawing groups. At this end, this is an electron donating group. Okay, so an electron withdrawing group would destabilize. Okay, if I had an electron withdrawing group here, it would destabilize. Okay. Well, maybe a better way to think about this is look, see, this substrate here is receiving electrons, right? So as a result, you would expect a plot like this, in which a cationic mechanism is in operation. Okay, so that's some of the evidence that supports this particular nucleophilic mechanism in this case.